Okay, good morning, everyone. I hope all of you are doing fine. So today we are going to talk about very important piece in semiconductors, which is the key semiconductor equations, right? So we have been seeing different physical mechanisms, and today we are going to see all of them. How do they come together and help us design the devices and even circuits based on these key equations, which are coming from the physical principles which we have been discussing. So, what we have been looking at, just to recap, we looked at there is a semiconductor, the piece of semiconductor which we have. If we want, and there are a lot of electrons or holes, let's say inside these semiconductors, and if we want them to dance in a sense that dancing is happening with the temperature anyway, right? But if we want them to contribute to a net flow of current, there are two mechanisms which we discussed in other two videos. One was applying the potential. So when we applied a potential to this, what we did is creating an electric field, and that electric field is what applied a force on this electron, let's say at the left electron, and this force in the opposite direction because it's a minus QE. And because of that, we saw that there was a net current flow which was happening. And this Jn is what we call as the current density. Right? Density means that it's the current, which is the charge flow per time divided by the cross section area which we are looking at. So that is your current density, one way to make electron flow. Another way which we saw, that the other way was that when we create a gradient which could be there, and we discuss different mechanisms by which this gradient could be. We discuss it could be a light, it could be your temperature, that you apply different heating at different places of the semiconductor which could create this flow. There could be light which is shining on one side which is creating this electron which we discussed in the last video itself of the generation recombination. So all of these physical principle is what is coming together today. So that means that there are electrons which are more at some side than the other electrons. And what is going to happen is we saw the very law of nature that something at one side is more than other, which is what we know as the concentration gradient, right? And we gave many practical example also, which is happening in real life when we are looking at this phenomena. And because of this, there is a diffusion which happens, right? And this diffusion is one can model, or this diffusion flux what we see can model as the dependent on the concentration gradient, right? Because this is a very physical insight that if I have more gradient, right, it is like I have more flow. So basically it is very similar to the analogy of the drift also. If you create more gradient in the, so there also when I apply in an electric field, it's basically I am creating. And we looked at the bottle of water. Bottle of water has a lot of electrons or a lot of water, right, which is uniform. Nothing is going to happen to the water if it is on the table. There is no flow, net flow of the water which you see in this. And we saw that when either we lift the water, lift the bottle in one side, then we see there is a net flow of water which would happen, right? So that is what we drew this case, that then there is a flow, which is what we are understanding as the drift, right? Or we saw that there could be that we create a membrane. That means there was in between there was a plug, and we filled a lot of water here. And when we remove this plug, then there is a water flow which happens, right? So this is what we named as drift, and this is what we named as diffusion, right? So that is what effectively we see these two phenomena which are coming together as a transport. So now the question is that, okay, if these are two happening, then how do we capture them mathematically, right? So one is, and these are the pieces are already there, which we have talked about in the drift and diffusion video. So we saw that this Jn, which is the current density due to electrons, is going to depend on the electric field which you apply, right? That is the other thing. And the other part is that how much charge is flowing. And then we gave an analogy that water flow is basically how much water you are having in the pipe and how fast it is flowing. That is what, how much you can collect, right, at one end. So that means there is a charge also which comes, right? And there is another quantity, and which is what we discuss this as a first as a velocity. And this velocity is what is described as a physical quantity, and this we will talk in another video because it cannot be justified in one video what is mobility, because it's a very, very inherent material parameter, right? It's a very material property. There's no external influence which you are having. You may change it within external influence, but it comes from the very inherent material property. So that's how you see, that means you are applying an electric field. There is a proportionality constant, which we are calling mobility, which decides your velocity of the electrons. So that means your current is mu E, right? Or mu N. Now, the question is, a lot of times we get confused in the sign, that is it negative or is it positive? And very easy way to understand that, going to your picture of this again. So what we are trying to say, because Q is positive for us, right? Qn is positive. Q is the charge or the atomic charge, right? And then we have the mu n E. So now there is only one variable which is deciding the sign of the J. So let's look at from the equation. If we go back to the picture, physical picture, we see that when we were applying electric field, your movement of electron was this direction. And we know that the current convention is that it's opposite to the electron. So that means your current is going to follow the same direction as your electric field, right? That is the simple way that you can see that this is going to be positive, right? Because a current is following the simple direction of the electric field. Now let's look at what is happening in the case of holes. Is it also in the case of holes? This is true. So when we have holes and you apply electric field, right? Let's say whatever direction we apply electric field, which direction would be the current? Because this is going to apply a force in this direction, right? F equal to QE. And then we know the positive charge, whichever direction it moves, there is a convention. By convention, we have the current also in that direction. So that is why you see the other component, which we are going to see, J is equal to QP mu P, right? This is the charge, this is the velocity. That is what is the water flow or your current which is flowing in the semiconductor. So now let's look at the other case. So these are the two equations. So based on that, you will see there is one equation, which is the total current, because we know that in a semiconductor, there could be both of them present. And that is what we have seen in the one example of generation, that when we are shining light, both electrons and holes are created at the same time. Similar to what we talked about, what is a semiconductor? When we apply a temperature, there are electron and holes, both are created. One is going from floor 0 to floor 1, right? So that means one electron, if it goes from one floor to another floor, Valence band to conduction band, that it also creates a hole, right? So that is why the total current is the sum of this two components which we see. So that is one clear equation which we see we have, which describes the current flowing in the semiconductor due to these two mechanisms, right? So now let's look, or this is what we call as the drift current, right? Now let's look at the other component which we saw, diffusion. Okay, what is happening due to diffusion? So let's look at this picture. So in this picture, we said, okay, it is going to be concentration gradient. Which concentration am I talking about? I am talking about the electron concentration. So now let's look at which direction is the electron concentration high, right? So if you see, there are more electrons here, there are less electrons here, right? So let's say N1, N2, and X1, and X2. So dn, your dn d by x is your N2 minus N1 divided by X2 minus X1. So all of this I am doing because so that you don't mess up the sign, so that you understand where the sign is coming from. And it's a very easy way to go again back to the physical picture and understand where the sign is coming from. So then you see the N2 is lesser in our case, which we have considered. X2, so that means N2 is lesser. So that means this is N2 minus N1 is negative. And what is this? Your X2 minus X1 is what? So that is also, we can see that this is positive, right? So and when we see this direction, because this is the x direction we are taking, right, you see that your dn by dx in this direction from left to right is negative. So what it means is, if I want to plot this, that on this axis my dn by dx is going to be positive in this direction, right? Because it is negative in this direction, so obviously right to left it would be positive. Now where is the flow of electron happening? Obviously electron flow is happening like this. Where is then jn will happen? J or electron current due to diffusion will happen in this direction. So now from this I see that my jn diffusion is actually going to be in the same direction as dn by dx. So that gives me that due to diffusion, my jn is going to be, and I know that it's proportional to dn by dx. And this proportionality constant is what we name as the your diffusion coefficient, right? And this we talked about in the physical meaning of this diffusion coefficient also in this. Okay, so then you see that this is the current, diffusion current due to electrons. Now let's see what is happening in terms of holes. When I have a lot of holes here, right, and I have a lot of holes here, let's again do this calculation of dp by dx. So where is the dp by dx more? So this is p1, this is p2, this is the x direction we are looking at. So dp by dx is again p2 minus p1, x2 minus x1. X2 minus x1 is positive, right? What is p2 minus p1 is negative, right? So that means this dp by dx is negative from left to right. So that means in this direction it is positive, right? dp by dx. Where is the electron? So this is the whole direction. That means your current direction will also be in this direction, jp. So now in this scenario, we see that jp is actually opposite to dp by dx. So that is the reason why you would see that you in diffusion case, you will have, or this will depend on minus dp by dx, which would lead to your jp diffusion to be equal to minus q dn or dp by dx, right? So that is the one way to check the signs in your equation so that you don't mess up. And we are going to talk more and more about these signs because mathematics is all about converting the physics into those formulas so that we can now calculate and design our devices which are based on these physical principles. So then we saw the diffusion current, total diffusion current would be dn by dx minus q dp by dx, right? And total J would be the sum of your diffusion current and sum of your diffusion current. So that is what is going to give us the total current density in the semiconductor. Now, is that the only thing that we need to worry about when we are solving semiconductor devices? And if you have seen the video of the generation recombination, then you guessed it right that it is not. It is not the only thing which can give us the current, because all of this when we are doing, we are assuming that there is a steady state which is there in your semiconductor. That means there is no time dependence, right? That means things whatever you have done to the semiconductor, they have neutralized, or that means they have settled after. So there's no dependence or time, right? That is what this thing will mean. Now the question is, when we were discussing generation recombination, let me give you the picture. So this is the box of silicon we were discussing. We said this could come, there is a light which could come, or either we could apply a temperature, right? High temperature, which could come from a burner. This will result in more and more electron hole pair to be generated. That is what we talked about. And there is another term which we talked about, which was R. We said, okay, electron hole pair is generated. Now it has to come back because electron will try to minimize its energy coming from floor 1 to floor 0. So that R, we talked about two mechanisms of that. We said it could be a radiative recombination, which is RR, and it could be a non-radiative recombination. And we said because there is a do physics because when it is losing energy, it has to lose energy by hitting other things, right? That's how it loses energy. Now if it is directly coming from floor 1 to floor 0 exactly at the same hole, then it is a radiative recombination, which is what means that there is a light coming out of our semiconductor. And when we see that it is hitting other atoms to come back and lose energy, is what we known as that heat coming out, which is why you see when you are having your laptops on your lap and this computation is happening and this recombination is happening every moment, you see the heat coming out of your semiconductor. That is what we see as the joule heating of your semiconductor, or the particular thermal resistance of your semiconductor, right? So now going back to this picture, how do we actually understand it mathematically? What is it telling us? So what it is telling us, in the end, we are only interested in, if you see, we are interested in N or we are interested in E, right? These are the two quantities we are seeing, because drift is telling me that you tell me two things. Let's say, let's look at the total picture. So J, if I have to calculate the total current, it is looking at either electric field importance or the charge, right? Or the concentration, right? This is what we looked at, which is what is giving us is J, right? These are the external factor by which this J is decided. And internally, obviously, those are the proportional constant of the materials. Now, the question is, we are saying, okay, but this phenomena is changing my charge. How do I take care of that? And that is where you need to bring in the time dependence into your semiconductor, which is what we know as the increase in this concentration per unit time, right? So that means if I look at this spot, this small box, I am looking at in this small box how my charge is per time is going to change. So now let's see what is happening in this box because of this charge is changing. What could happen in this box is, obviously we see when there is a flow of electron happening, so that means our current J, which is coming in and coming out, right? So J in coming in, J in going out, that itself can result in this dN by dt change, right? Because some electrons are moving into this box, some are leaving this box, right? So that is what is our Jn itself. What else can happen to this box? Why, which, due to which the dN by dt will change? Obviously, as we saw, other factors like light, other processes, light, temperature, whatever those are, they can also result in, which is what we know as the generation of these due to these processes which could happen. What other things? Thermal generation recombination is anyway happening, which we know as the thermal. So this is because your temperature, whatever your semiconductor is setting, is not setting at 0 Kelvin. So that means generation and recombination is always happening in your semiconductor if it is not at 0 Kelvin. It is always happening. You know it or you don't, but it is always happening, right? So that is, these are the thermal generation and recombination which we have, right? So now let's see how this comes into all being, because now we understood what is happening. So if I want to find out a net dN by dt at some point, what would it depend on? First of all, it would depend on how much my current or density is changing from this x to this x. So we are just looking at in one dimension. Obviously, this is all true in multiple dimension. But let's say in one dimension, if I look at how much current is changing from this to this. So that is what brings the, you guessed it right. What would it bring? Which quantity would it bring? Is the gradient, right? Because now we have to look at this Jn1 here or Jn2, how much it has changed. So that would give us the gradient of the current, right? That is what, and this is 1 by q. 1 by q means because we are only looking at the density. We are not looking at the charge, okay? So n is our density. It's not charge yet. Charge is when you multiply with q. Then other density or the generation is what will come, J minus R, because G is the generation, recombination, whatever is recombining, right? So whatever in this box is also generating and recombining, right? That is what we saw. It's a birth, cycle, and dead, right? That is what G and R, which is always happening in your semiconductor. Now this G and R, one can expand that. They can say, okay, this G is through thermal, this G could be due to light, right? So all of this can be expanded in these terms because there are multiple processes which are coming. Similarly, we could write similar equation for your holes also, right? Okay, this is the very same thing, that how many holes are entering, how many are leaving. So these are this very important set of equations which are known as, if you guessed it right, they are known as continuity, because that is very similar to the water flow. When you used to study, we used to apply, okay, how much water is entering, how much is leaving, right? Because we have to keep account of that, right? If we are putting 10 electrons, where are they going if 9 is coming out? So that means one is somewhere being lost. It's not magic. It has to be accounted in the generation and recombination process. So there is no magic happening that by magic it has gone away. We have to keep account of how many electrons we are putting in this box, how many are coming out. So that is what leads to these very key equations are known as continuity equation. So you already see, if we consider a case of steady state, and steady state we have talked about, and we can talk about it in another video if you are interested in what is steady state, what is equilibrium. So steady state is the key, that there is no time dependence. That means everything is settled, right? For a long time things have happened, all the perturbations have happened, now things have settled, right? That is the time. So it's everything is taken care of, initial, all the initial iteration. So these quantities what we see, they tend to zero, right? That is what the key steady state, and that is the thing that we see, that there is a constant current. That means the Jn1 and Jn2 would likely to be same, right? Or this is equal to, from this we can say that it would be equal to G and R. So let's say in the box, if we say G and R is zero, that means your gradient of current is going to be zero. That means your current is same at every point in semiconductor. Because if we assume at every point in semiconductor, G and G is equal to R, right? Then your gradient of the current is going to be zero. That means your current is going to be constant. And that is one of the thing when we ask who is evaluating semiconductor devices, is your current continuous or not, right? So that is the current continuity, or known as current continuity in semiconductors, because that is, or it is coming from directly from the continuity equation. Okay, so now we have seen the transport equation. We have seen how is the current or these carrier generated if there were different processes. Now there is one more important thing left, and I would not spend too much time because you have probably gone through 12th and where you have studied. Okay, so good. You are saying there is electron which are there in the semiconductor, and you are saying that I am applying this field, which is an external field, right? This voltage is applied, which is giving you this field, which is an external field, which is making it move. But you are again saying that this current is dependent on electric field, right? So now the question comes that if I'm interested in calculating this current at this point, right? This is my JNX1, if I'm interested, because that is what is defining my current continuity, right? I saw in the continuity equation that I need that Jn at every x. So then how do I calculate this E, which is x dependent? Because I am only applying the V, which is outside voltage. But how do I know that how is the internal field coming from? Where is it coming from? And then comes a very important physical principle, which you would have probably heard, that every point charge is generating a radiating a, because it's a radiation, right? It's like your face, it's radiating light. Similar to that, a charge, a positive charge will radiate, which we know as the electric field. Or in the negative, the convention is that it would absorb, right? That is what the convention is. So now from that, you can say, oh, if there is some charge at this point, right? Now we are not dealing with the point charges. Obviously, there is a some charge which is there, which we know as, for example, this charge, we can say it's a charge density, right? And we have talked about what does it consist of in another video when we talked about what is semiconductor. So depending on, you have electron and holes, it would consist of electrons, holes which are positive, your electrons which are negative charge, right? That's why negative sign. Then you have your holes, sorry, your atoms which are giving you this charge, right? So these are your dopant atoms which we talked about, and we will talk about it in other video, that where what is doping. So that is still left. We have not talked about what is doping, but the rho can be thought as the total charge at one point in X which you are trying to look at, right? So that is the charge density. So that is what you are looking at in this. So then one can see, okay, how do you calculate the electric field based on this charge density? How do I even know that? And that your famous law which you would have studied, Gauss law, which tells this exact thing what we have studied, or this is the law which defines all the electrostatics which we have seen, or you have seen in the different books in physics, right? Where you saw that, okay, the charge now it has to relate to the electric field. So that means I need to know that if there is a charge at this point, how much electric field it is generating around it, right? So let's take this positive charge. We know that it is radiating electric field, right? Now, first of all, we know that this electric field is going to change as we go far from the charge. So that means already, if this is my x1, this is my x2, I know that this charge or the electric field has to be related. So there is a gradient of this thing has to relate with rho, right? That is what would result from this itself. Now the question is, how do we relate these two quantity, the gradient of the electric field and the rho, right? So rho is the charge, which is the positive charge. So here, let's say this at this point, it would give E1 and E2. Again, I'm telling this in the way because people do make mistakes in the sign. So once you understand the physical picture, I don't think you will ever make this mistake of sign, because you will always go back to the physical picture. You say, oh, this is the field, and this positive charge is giving field outside, because that is what we know from Gauss law, that it is giving outside field, right? Or the convention. Negative charge will absorb the field. So the field lines would look like this, E1 and E2. So now this is what we have to relate. How do we relate? So one thing is, there is one important proportionality constant which we again will bring, because this is all about proportionalities, right? There is a quantity which is changing, output quantity. We want to relate it with rho. Can I just directly put dE by dx equal to rho? No. There is another physical quantity of the material which comes into picture, which what do you guessed it right. What do you call it? Think of it. In a material, if I have a charge which is creating an electric field, how much electric field is created due to that charge? What is that quantity which you have used in electrostatics all along? It's called your dielectric constant of the material, right? So this is the proportionality constant which we see as the dielectric constant of the material, which is what tells us the susceptibility of this field. So now the question would be, what would be this sign? It would be positive or negative. So let's look at positive charge, because we know rho is positive, then the dE by dx should be positive. If it is positive, the same direction, that means this sign is okay. So let's see this thing. If it is positive, what is dE by dx? Obviously x is in this direction. So dE by dx is E2 minus E1 divided by x2 minus x1. E2 is positive? Yes. E1 is negative? Yes. So this quantity is going to be positive. X2 by x1 is positive. Very good. So that means this guy is positive. Now let's check for negative sign. It should hold also for the negative sign. So that means E2 minus E1 divided by x2 minus x1. What is it? E2 is negative or positive, because it is in the direction, opposite direction. So this is negative. This guy, negative, negative, this is positive because it's pointing to the right, right? So this is positive. So then we see this is going to be negative, right? So dE by dx, if we see, it's going to be negative. So that is also reflected from rho, because rho is negative. So that is how you see that rho and dE by dx, they follow the same sign. Very similar to the diffusion analogy which we have seen just now, right? So that is one of the key equation which you would see now. dE by dx is equal to your rho by epsilon. Now you will say, okay, that is very good, but you told me, okay, that means now I can relate my electric field to my charge by this relation. And then from charge, I know when the charge is there at a particular point, I know what is electric field. And when I put that electric field in my drift equation, I can get the current. Wow. So that means now you are seeing that all of these basic equations, one is how much a particular charge is radiating the field, that gives me the field. Now, given that there is a field, we know how much is the drift current. And then when there is a change in the concentration, we also know that how much is the diffusion current. All of this coming together gives us these basic set of equations, is what we know as the semiconductor equations. So these are the ones which are basically solved in any software which are solving the semiconductor devices, which we know as the TCAD softwares. These are basic 5 equations which are solved in a TCAD if we are dealing with all the classical physics of semiconductors. Right? Obviously, if we are going to nanometer scale devices, this will change. There are some things which needs to be added on top of that, but these will still remain the workhorse of the semiconductor devices. 1 and 2, we have seen the continuity equation, and we have seen the drift diffusion equation and the Poisson equation relating the electric field to the charge. Okay, so with that, I would end this video, and happy learning to all of you. And if you have questions, please post it or you can email me. Thank you.